Okay, welcome to what should be the last of our Chapter 11 videos. And this last topic in Chapter 11 deals with stress concentrations. So up until now, we have been operating under the assumption that the materials that we are stressing, that we're putting under stress, don't have any interruptions in their cross-section. So for example, I have a rectangular bar, and I apply a load to it. I've got a load of P, and the assumption then is that the stress is evenly distributed across the cross-section here. So it's the same amount. It's the same amount of stress at this edge and at this edge and in the middle. Everywhere where I measure the stress, it's the same amount. And I'm graphically representing the stress here with this shaded region with the horizontal lines. Well, what happens is if we drill a hole in our material like we have over here, what happens is it causes that stress that was nice and evenly distributed to now be unevenly distributed. It causes the load to, or the stress to spike and then trail off towards the edges in this hyperbolic way. So we see a spike in stress, maximum amount of stress occurring at the edges of the hole, and then considerably less stress near the outside edges of the part. If we were to cut some semicircular grooves in either side, we would see something similar happen. Where we have interrupted the cross-section, we now see a spike in stress levels, and we see this parabola here where there's a minimum amount of stress in the center and maximum stress levels near the semicircular grooves. And the last example here we have is a large cross-section, and then it has these radius fillets that reduce the cross-section from the large to small cross-sections. And again, we see maximum level of stress occurring where we have interrupted the cross-section of the member, and this parabola here, so we've got a minimum amount at the center, and near the outside edges a maximum amount. And the average amount of stress it is affected as well in each of these three situations because we've reduced the area. Stress is load divided by area, and so if the area gets smaller, the stress is going to get bigger. So when we have one of these 1, 2, 3 situations where we have either a hole drilled into it, grooves, or a reduction in cross-section with fillets, we want to know what is the new average stress and what is the new maximum stress. So the average stress is going to be affected just because we have smaller area, and the maximum stress is going to jump up because of the interruptions to the cross-section. So the way we do that is by using a chart in your book that looks like this. Now, the maximum stress is going to equal a coefficient K multiplied by our load divided by the new reduced area, or net area. So if we take K times load divided by area net, it gives us the maximum. And the average stress, undo that, let's try that again. The average stress is just going to be equal to the load divided by the net area. So if we find the new average stress, all we need to do is multiply it by K, and we've got our new maximum stress. Now what is K? K comes from this chart. So we have the three situations here. We have a hole that's drilled into it. We have the two semicircular grooves, and we have a reduction in cross section. Those correspond to these curves, one for a circular hole, semicircular groove, and fillets. So we need to find R over D along the horizontal axis, follow that up until we hit the curve of whichever three situations we're investigating, and then come over here, and along the vertical axis we have our K values. So R over D is equal to the radius divided by the net width. So, for instance, when we drill a hole, we are removing the diameter of the hole. So we had the original D. If we subtract from it the diameter of the hole, which would be 2 times its radius. So the hole has a radius. That's the radius part. And then the net width is going to be the width minus D. Or rather, I should say the width D, the original width D, minus 2R, because that is the diameter of the hole. So the hole diameter equals 2R. So in this case, the net width, little d, is going to be equal to the big D minus 2R. Over here, we're subtracting a radius here and a radius here. So again, the net width, little d, is going to be the original width that we start off with minus 2R. And over here again, it's going to be the big D minus, we subtract one radius here, another radius here, minus 2R leaves us with the net width. So let's try an example. I'm going to scroll over and up. And here we have the image from example 1115 in the textbook. So here we have a rectangular structural member that has a tensile load of 4,000 pounds being applied to it, but we have now drilled a hole into it that has a 3/4 inch diameter, which means we have a 3/8 of an inch radius. The original width of this, the big D, was 2.5 inches, but we're going to subtract from that 2 times the radius, or 3/4, to get our net width. So the net width is going to be the big D minus 2R, so that's equal 2.5 or 2.5 minus 2 times the radius is 3/4, 0.75, and so that's equal to 1.75 inches. So now I can find R over D. The radius of the hole is 0.375. The D net width we just calculated as 1.75. And so 0.375 divided by 1.75 gives us 0.214. Now, a mistake I sometimes see is students thinking that this value is equal to K. It's not. This is just R over D. What this allows us to do is then refer to this chart from the book. Okay, and let me switch colors here. Maybe a color that will show up better in this white background. And so our R over D was 0.214. So here's 0.2. This would be 0.25. And so 0.214 is probably about here. So we're going to follow this up, and we're not dealing with fillets. We'll skip right past that curve. We're not dealing with semicircular grooves. In our problem, we're dealing with a circular hole. So if I then come over horizontally, there is some room for interpretation here, but because it's somewhere between 2.2 and 2.4, I would probably say that K is equal to about 2.3. So there is some room for interpretation. If you say it's like 2.35 or something like that, that's okay. Your answer will be slightly different, but it will be pretty close to agreement with the solution here. So we're going to go with K equals 2.3. So I'll slide over here and up, back to this example problem, and we've got K equals 2.3. So the depth of this block the whole time has not been affected. This depth is still 3/8 of an inch. You can see that's given up here, or 0.375. So the net area is equal to the net width times the thickness. So the net width we said was 1.75. We multiply that by 0.375 inches, and 1.75 times 0.375 gives us 0.656 square inches. And so our new net average stress, due to our reduction in cross-section because we drilled a hole in it, is going to be load divided by area net. So the load is 4,000 pounds. The new net area is 0.656 square inches. And so this is equal to 6,100 psi. That is the average stress. Now to find the maximum stress, we take this average stress and multiply it by K. So K is 2.3, and the average stress is 6,100 psi. And so 6,100 times 2.3 gives us 14,030 psi. So that stress is going to jump way up at the hole. If I were to represent that stress graphically here, and that maximum amount of stress here is the 14,030 psi. But if I take somewhere the average value here between the maximum and the smallest amount, the average stress is our 6,100. Okay, so that's how we find both the average and maximum stress when we do something like drill a hole in a tension member. Okay, I think that does it for Chapter 11.